Okay, so in this video, we're going to find the equation for the tangent plane to a surface of the form z equals f of x, y at a certain point. So this is a little bit more interesting function than the more simple ones that you see that's first or second examples in a calc class. So I have used geogebra here to graph it. I have here on the left the point. I haven't found out what the z value is on purpose. So I graph this in my graphing. So this is the surface. Let's find the point and graph the point. So you see it's a little bit more interesting than the typical surface. And there's no way, it will be very hard for us to see level curves or to identify the surface, what it looks like. So none of the techniques we use about level surfaces or level curves, sorry, would help us identify the surface. But nonetheless, we can figure it out in 2020. When I'm posting this, we have the tools to visualize what's going on. Okay, so at the point when x is 2 and y is 0, first I'm going to find what is the z value. So the z value, what I'm looking for is f at 2, 0. So that's the output of this function. So it would be 2 times e to the 0, right? I'm plugging in x and y into this function above. And then it would be 0 times e to the 2, e to the negative 4, sorry. So it doesn't matter, that's a 0. So this is 2. E to the 0 is 1, so the point is the 2, 0, 2. So let's go back and just plot the point to see where that is. I have it here. So it'd be the 2, 0, 2. And if I press enter and I update it, so there's my point. You see a little circle there. GeoGebra calls it a point A. It's right there. Okay. Okay. So that's my surface, and that's my point. So now let's find the tangent plane. Okay. So the plane is going to be a plane that goes to that point, and you might already guess what the plane looks like, right? I'm not going to give up to it, but let's see what the plane looks like. Okay. So the form that the equation of the plane looks like, hope you've seen that by now. I'm just going to use it. It has the form z minus z0 equals the partial f at the point, x0, y0 evaluated, times x minus x naught, and then the same thing for the partial f respect to y evaluated at the point, times y minus y0. So there's an explanation of why this is the tangent plane to the surface. So there's another video where I explain this, what this happens. Okay, so all we're going to do now is find these partial derivatives. So who is, I'm going to scroll this a little bit here so we can still see the function. Who is the partial of f with respect to x? So I'm using the partial derivative of this function with respect to x, so the y becomes a constant, anything with the y, so e to the y squared is a constant. So the derivative of f with respect to x is x, oops, sorry, wrong pen. It's 1, because the derivative of the x is 1, so it's just e to the negative y squared, right? And then this part over here, I still have to find this derivative on this part. It's the derivative of the power e to the negative x squared, which becomes negative 2x, and have the y, which becomes a constant, and then times e to the negative x squared. Right, so I find the derivative of this function over here. So my x squared is my variable, so the derivative of that becomes a negative 2x coming in front because of the chain rule, and then times e to the u, which is e to the negative x squared. Okay, so that is the derivative of f with respect to x. And now I need to find the derivative of f with respect to y. And now I find the derivative of the first term with respect to y, right? And now the derivative of x, sorry, x is a constant, so now it's similar to what I just had before, right? I'm going to have the negative 2xy e to the negative y squared, because the derivative now it's the y part, so it's negative 2y comes down because of the chain rule, and now the e to the negative y squared stays there. And now the derivative of the second term of this one is just the y is a variable, the other terms are constant, so it's just plus e to the negative x squared, correct? Okay, so if I plug in here, now what we need to do is plug in the point. So I'm going to find now who is the derivative with respect to x at the point 2, 0. That's x and y. So at the 2, 0, this is e to the 0, so it's a 1. And this becomes a 0, right? Because y is 0, I'm going to plug a 0 in that y, so that's a 0. So I just get a 1. Okay, now the partial of f with respect to y at the same point, evaluated at 2, 0, is going to be, the y is 0, so now this term is 0, right? And I have e to the negative x squared, so it's e to the negative 4, like that. So I got everything I need to find my tangent plane, right? So the tangent plane this is the form of the tangent plane, and I have all the ingredients now. So let's write down. So the tangent plane will finally be z minus z0. I found it over here. The z0 is the 2. So z minus 2 equals partial f with respect to x, which is just a 1, times x minus x0, which is a 2. I'm getting that from up here again, the point, right? And now it's plus the partial f with respect to y, and that was e to the negative 4. I'm going to write it like 1 over e to the 4, okay? And now it's time y minus y0, it's y minus 0. And that's it. That is the equation of the plane. Let's work this out. So I really have z equals x minus 2 plus 1 over e to the 4y. And this 2, I'm going to move to the other side. So I have another 2. So I really end up having it cancels, right? Adding a 2. So that cancels this term. This is on the other side of the equal sign. So we just hit the plane, oops. We just get the plane z equals x plus 1 over e to the 4y. Okay, so that's my equation of the plane. And let's check it out now in my graph. So this is the cool thing about doing this in the year 2020 that, well, I don't know if you had this example and you learned this, maybe if our parents took this class or your grandparents took a Calc 3 class and you were graphing this, you would follow the instructions. Everything looked fine. You got the tangent plane, you got the surface, but it was going to be very hard to see this, right? To visually have a visualization of what's going on. So why don't we use that power that we have now? So if I use GeoGebra for this, now I have here to put the plane. The plane is just we said it's x plus, let me see if I have it correct. I have it written down here. It's plus y divided by e to the 4, correct? Let me double check this we got. Yep. So I'm going to put here plus y. Nope, wrong. Plus y divided by e to the power of 4. And it's graphed. So there it is. So this is the plane. Looks like there, a tangent at the point A that we had. And it's this red plane that is right there. It's a little bit transparent so you can see it, right? So basically, if you see it right here, this is what I said maybe you saw before. Any point along the line, any point of the form on the x-axis, positive, 2, 0, are the one I use. So I guess 3, 0 would have been up here. It would be the same plane, right? That would be an interesting problem to show that for any, maybe above and maybe after 2, 3, it's the same plane. But that's a conjecture. We can just still have to do the algebra to do it. Okay, so this is a cool example to visually see the tangent plane to an interesting surface.